So here we go. We'll jump into this rational function, our first rational function, and begin going through the process of analyzing it one by one. We're going to tackle each of these questions, okay? So let's switch over to pencil and paper here. The first question says, here's our function. First question A is to determine the restricted values. I'm just going to put RV for restricted values. And write the domain of the function, okay, in interval notation. So here, you have to be able to remind yourself, how do I find the restricted values when I'm given a rational expression or a rational function? What do I need to look at? Which part of the equation? Which part of the function?
The denominator?
The
Denominator.
denominator. The denominator is exactly right. So for the restricted values, I only care about the denominator, okay? So you don't want to make the mistake of freaking out and then saying, oh, I'm going to set everything equal to 0. Don't do that. We just want to focus on what is relevant. Restricted values come from the denominator. So what we're going to do is set that up. We're going to go with x squared minus x minus 20 equals 0. Are you guys okay with that?
Yes.
Okay, can you tell me what kind of an equation this is?
Quadratic.
Okay.
It's quadratic. So again, I prefer to factor these when possible. And just for time's sake, just to save on time, I'm going to use the quick method for factoring this, okay? Remember, I can only use the quick method when my first coefficient a is a 1, okay? So this is going to factor into x
Plus 4. X
plus
minus 4.
4 and minus 5, okay? Because remember, that quick method just says, oh, we really just want to look at the factors of negative 20 that are going to add to give us this negative 1. And if I have a positive 4 and a negative 5, that's going to multiply to make the negative 20, and it's going to add to give me that negative 1. Okay? So we're just doing the quick method. So if these are my factors, I could set them equal to 0, right? And I'll just go ahead and show all the steps. X plus 4 equals 0, and x minus 5 equals 0. But these are really nice, simple linear equations. And I know that this is going to give me x is equal to negative 4, and x is equal to positive 5. Are you guys okay with that?
Yes.
Okay. Because at this point we have a lot of tools in our toolkit, and where possible, we want to sort of whip through some of these problems so that we're not spending too much time worrying about, well, what if this and what if that, right? These are our two restricted values. Okay. So I'm just going to put here, these are my restricted values. And then the second part of this question asks to find the domain. Okay. So remember, for the domain, what we do is draw a graph of your number line or your x-axis, right? And then we're going to plot our restricted values. So we have negative 4 here and positive 5 here somewhere. Doesn't have to be perfect. My number line goes to negative infinity on the left, positive infinity on the right. And if you remember this analogy that I talked about yesterday, we think about, or maybe it was the day before, we think about the number line as a piece of rope. And if I'm cutting these two numbers out because they're restricted, if I'm cutting those numbers off of the number line, how many pieces do I have in for my number line now?
3.
I have 3 pieces, right? So if I just write the interval notation of those 3 pieces, that's going to be the domain of my function. So this piece goes from negative infinity to negative 4. and those are going to be both parentheses. Then the middle piece is going to be -4 to +5, right? And then the last piece goes from 5 to infinity. So sorry, that's a parentheses over here, sort of running off the page. But that's it. That's the domain. So if we can find the restricted values, that should help you visualize the domain if we go ahead and draw that number line and make the cuts where we need to put them. Any questions about that first question or that first part? You guys feeling okay there? Vibe check? Okay, sounds good. All right. Anybody still writing, or are we able to move on to the next part?
Could you just give me one more moment to finish writing it off?
Yeah, you got it. I'm going to take a strategic sip of water, stall for time. You got this. Okay, I'm just going to write the next question down. B says to draw the vertical asymptotes. And just let me know when you guys are ready to tackle this new vocabulary word, this next question.
You can go ahead. Thank you, sir.
Okay, cool. All right. Draw the vertical asymptotes. So what you have to understand here is that we have a new vocabulary word, and that's vertical asymptotes. The vertical asymptotes, or I'm just going to put VA here just to abbreviate it. Vertical asymptotes are gaps that appear in the graph where the restricted values occur. Okay. So that's one definition. We can think about vertical asymptotes as being these vertical gaps where the restricted values are. Okay. So when you get to a question like this in ALEKS and it asks you to find the vertical asymptotes, it's often going to say write the vertical asymptotes as an equation. And when you see that, write the vertical asymptote as an equation, you're going to put x is equal to some number. Okay, so this is going to be similar to, if you recall, the axis of symmetry when we were studying quadratic functions. So if you recall the axis of symmetry.
I totally missed that in my class. In my test, I put the number and I didn't put x equals.
Oh, okay. Well, if you wrote it down on your work, I'll go back and take a look at it and make sure that you get those points back. Because a lot of times students won't put that x equals, but they know what the value is, and I'm going to say that's not a big deal. Okay, so for the axis of symmetry, when we had like a parabola or a quadratic function, we said, okay, the vertex is in the middle of the graph, and then we just said the axis of symmetry is kind of like this imaginary line that we project onto the function, and it's a vertical line that cuts the function in half. Okay, well, similar to that, the vertical asymptotes will cut the graph into sections. Okay, similar to what we talked about up here for the domain, right? So like this equation that we're looking at, this function, when we asked what's the restricted value, we found two restricted values. So that means that when we found the domain had two cuts that we had to make to the number line, which left us with three pieces. So when we start graphing these functions, the vertical asymptote, since we have two of them, is going to cut the graph into two sections. Okay. So what I'm going to do is on another sheet of paper, I'm going to start the graphing process. Okay. So if you have graph paper or line paper, it doesn't really matter. This isn't going to be perfect. Okay. But I'm going to draw this nice and big so that we can see it. Here's my x-axis.
If we printed out the worksheets, is this where we draw it on?
Yeah, you could draw it on the worksheet for sure.
Okay.
I just didn't print it out myself, and I didn't expect everybody else to have a printer. And also, I just posted the worksheet before we started class. So if you're already printed it, great. But I don't think everybody has the same luxury. So drawing it is fine. Okay, so we have our x-axis. We have our y-axis. And I'm just going to go out like maybe like 5 or 8 units in each direction. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it doesn't have to be perfect, just good enough. Okay. Now this question said to draw the vertical asymptotes. But first, we need to know what the vertical asymptotes are. Okay. Well, here we go. For our graph, and I'm going to go ahead and say this is not relevant here. But what is relevant are these restricted values that we found earlier. Because it turns out that for our graph, the vertical asymptotes are going to be x equals the exact same numbers as the restricted values. So -4, that's our first vertical asymptote. And x equals 5. That's your second vertical asymptote. So in reality, vertical asymptotes are the same as our restricted values. So there's not more work that we have to do here. We just have to remember that when we're asked to find the vertical asymptotes, that's the same as finding the restricted values. Okay? So I'm going to put here, same as your RVs. Questions, comments about that?
So, Mr. Aguilar,
Yeah.
so essentially, like the restricted value, like the equal sign, you slash it, you just remove that, and now
Yeah,
it becomes
exactly. So when we call them restricted values, we want to say our solutions can't be these numbers, and that's why we put a slash through it. But for the restricted values, just like you said, we remove that slash, and then those are our equations for the vertical asymptotes. Does that seem easy enough to do? Right, and so this is kind of like, I think it's very similar to when we started studying quadratic functions, we had to find the x-intercepts, and we called them find the x-intercepts. But then when we got to polynomial functions, we said, oh, find the zeros. And we were calling x-intercepts by a new name, right? So when we first started studying these, we called them restricted values, and we wrote them with the little slash mark through the equal sign. But now that we're graphing them, we're going to call them vertical asymptotes and remove those slash signs. Okay. So just calling an old friend by a new name. But when we graph this now, we said that the vertical asymptotes were at -4 and +5. So what I'm going to do is go to my x-axis, and I'm going to find -4. So that's going to be 1, 2, 3. That's -4 here. And at that -4, at my restricted value, I'm going to put a dashed vertical line And I'm doing this in red ink because this is going to be like a boundary that my graph cannot cross, right? Because -4 is a restricted value. So the way that appears on the graph is going to be, there's going to be a gap where my graph will not cross this line. It can't cross that line because if I were to plug -4 into my function, it would zero out the denominator and I would have undefined. I wouldn't have a y value. Okay. So this is where it's all sort of conceptually coming together, this idea of restriction, this idea of getting a y value and graphing it. So we'll see in a second what the rest of the graph looks like, but we want to set up our vertical asymptotes. The other one was at +5. So we'll go to 1, 2, 3, 4, 5. This is +5 here, and we'll put a vertical line. Just a little dash line, just a visual aid to say that that x value, x equals 5 and x equals -4, those are technically restricted, okay? So that's what we mean when we say draw the vertical asymptotes. Just draw those little dash lines. Any questions or comments there? Does anybody need more time to sort of write this or draw this out? Okay. So part C says determine the horizontal asymptote if any exists. Okay. So right away, the wording of the question seems to suggest that sometimes you will have a horizontal asymptote and sometimes you will not have a horizontal asymptote, okay? So here, the horizontal asymptote, even though it has the same or similar sounding name to vertical asymptotes, we haven't learned exactly how to find these. It's not as easy as saying, oh, it's part of the restricted values. So it's going to be a little bit of an involved process. So to find the horizontal asymptote, what we need to do is look at your original function. Okay. So the original function that we had was kind of a complicated thing, but I'm going to rewrite it. It was x squared on top plus 6x minus 7 over x squared minus x minus 20. Okay. And the first thing that you want to do before finding the vertical asymptote is you want to answer this question. Remember that I said these rational functions have a polynomial on top and a polynomial on the bottom. If we have a polynomial on the top, that means you should be able to tell me what the degree of the polynomial in the numerator is. So I'm going to put degree n for the numerator degree is equal to what?
2.
2. Right? Because remember, degree means what's the highest exponent on that variable x. Okay? So if you can tell me the degree of the numerator, you should be able to tell me the degree of the denominator. So I'm going to say the degree of the denominator, we're going to call it d for denominator degree. So what's the degree of the bottom polynomial?
2.
2.
Also 2. Okay, because that highest exponent is a 2. Okay, so we kind of have to go through this checklist, find the degree of the numerator and the denominator, because there are 3 cases that we need to be aware of for the horizontal asymptote. So I'm going to write it this way. We have case A, we have case B, and case C. So this is like a cookbook. Think about it that way. If you have this situation, you'll do the instructions for part A. If you have a different situation, we'll do the instructions that I'm about to give you for case B. And if we have another situation, you'll do whatever the instructions are for case C to find that horizontal asymptote. Okay.
So we're not always gonna do
You're
all
not
th-
always going to do the same thing.
no, we're not always gonna use all three cases. We gotta figure out which one to use.
That's exactly right.
Okay.
Yeah, you always have to figure out what case am I dealing with, and then if I'm doing case A, then I'm going to ignore case B and C. I don't have to do those,
Okay.
right? So how do you know which case you're dealing with? Well, it's based on the degree of the numerator and denominator. So if the numerator degree n is equal to the denominator degree d, then you're dealing with case A. Okay, and that says the horizontal asymptote is y equals, and then we have a fraction here. And I'm just going to write this down and I'll explain it in a second. LCN over LCD. Okay. So case one, or case A rather, says if my numerator and denominator degree are the same, then the horizontal asymptote can be found by this equation. Y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So LC here means leading coefficient. Okay. So I'm sure that some of you guys will notice that we are dealing with case A in this problem, but I want to give you the instructions for case B and C before we really dig in. So case B is if the numerator degree is less than the denominator degree, then the horizontal asymptote is y equals 0. So there's no math that we have to do with that one. Okay. If the numerator degree is a smaller number than the denominator degree, then your horizontal asymptote is automatically going to be y equals 0, and then we can go draw that on the graph. Finally, if the numerator degree is greater than the denominator degree, so if the numerator degree is a bigger number than the denominator degree, then there is no horizontal asymptote. Questions, comments? I know that's probably a lot of writing, so I'm going to give you guys a moment. Okay, you guys ready to dig in? All right. So the first thing you always want to do is assess what the numerator and denominator degree are. Okay, because that's going to help you choose which case you're dealing with. And I don't expect you guys to memorize this. So like this is kind of what you would need to put on your note sheet because it's kind of a lot to remember, right? But looking at our numerator and denominator degree, which case are we dealing with?
Case A.
Yeah, so for this one, we're dealing with case A. Okay, so then my instructions are, if the numerator is equal to the denominator degree, then the horizontal asymptote is going to be given by y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, so what is the leading coefficient of the numerator?
1.
1.
Yeah. So if you remember that when we were talking about polynomials, I said this is the leading term
Mhm.
and its coefficient is a 1. So I'm going to put up here y equals 1 is your leading coefficient of the numerator. What's the leading coefficient of the denominator?
Also 1.
Also 1, right? So what is 1 over 1?
1.
Yeah, y equals 1. That's your horizontal asymptote. Okay. So like there's some background information that we need about these cases, but as long as we can identify the degree of the numerator and denominator, that's what helps us choose which case we're dealing with. And then once we're in that case, we can ignore the instructions in the other ones and just try to figure out what do I need here, right? Since we were dealing with case 1, we looked at this kind of formula that we had here, put those numbers together by taking them out of the equation, and 1 over 1 is just 1 in this case, so that's really nice and neat, okay? And it is very much that simple. So for instance, if I had, hypothetically, like a 2 here on top and a 3 here on bottom, if the degrees are the same, then my horizontal asymptote is 2 over 3. It's just that simple. Okay, so don't make it more complicated than it has to be. But obviously, this is going to take some practice and some work before we start to feel a little bit more confident. This is the first time we're seeing it, so don't feel bad if it's feeling like kind of shaky right now, okay? Any questions, comments before we move on to the next question? Okay, so I'm going to bring my graph back in here, right? And we set up the graph with our vertical asymptotes. And we said that the horizontal asymptote was at y equals 1. So on the y-axis, at 1, I'm going to make a horizontal dashed line here. And then this is going to be like another sort of boundary for my graph, kind of. But that's the horizontal asymptote y equals 1. Okay, so this is my horizontal asymptote. And these are my vertical asymptotes over here. Are you guys okay with this graph that we're sort of slowly building up to?
Yeah.
Yes.
Okay. Now these asymptotes have sort of divided up the graph space into really 3 sections from the vertical asymptotes. We have this left section, this middle section, this right section, and then the horizontal asymptote kind of divided that up into 2 more sections. So now we have our upper sections and our lower sections, okay? So we're going to see how we can plot our points and graph things here in a moment, but the next question is asking us to find the x-intercepts and the y-intercepts. So I'm going to go off script because the paper, the handout says find the x-intercept next. But I think that the x-intercepts are a little bit harder to do. So I'm going to skip D, and I'm going to do E first, which is find the y-intercept, because that's always going to be easier whenever we're talking about a graph. So I'm going to put E here, find the y-intercept, and there's only ever going to be a single y-intercept for any of these functions, okay? So that's really nice. We're not looking for multiple y-intercepts because then that wouldn't be a function. Do you guys remember how to find the y-intercept for quadratics or polynomial functions? What was the process that we used?
It was
Plug in the 0.
plug in the 0.
Yeah, so we're going to say x is equal to 0 and
0.
plug that in. So we need to bring our function back, which I'm going to sort of zoom out so we can see the function up here. We're looking for f of 0, which just means that we need to put 0 squared plus 6 times 0 minus 7 on top, and then 0 squared minus 0 minus 20 on the bottom. And then if this looks super intimidating, what are we going to do?
Calculator.
We're going to grab the calculator. Okay. So if that feels like a really daunting task to try to have to do that in your head, and if you're feeling burnt out by the end of the day, definitely grab that calculator. Don't be a hero. So I'm just going to put a fancy fraction in here. I'm going to type it exactly the way I wrote this down. 0 squared plus 6 times 0 minus 7. Okay, and that's a minus 7. Don't get confused with the negative 7. Okay. Then we have 0 squared minus 0 minus 20, and then we can hit enter. And I got 7 over 20. Well, that kind of makes sense because if you were to do this by hand, 0 squared is 0, 6 times 0 is 0, 0 squared is 0, negative 0 is 0. So all of these things that got multiplied by a 0 canceled out. And then a negative divided by a negative turns into a positive. So all you're left with is positive 720 or 7 over 20. Okay, so that's the y value, which means our y-intercept is at 0 because that was our x. And then 7 over
720.
Okay.
So,
But since we're graphing this by hand, I guarantee you that nobody here off the top of your head, myself included, I have no idea where 7 over 20 is. I don't know what number that is. So I'm just going to switch this, since we're graphing by hand, to 0 comma 7 divided by 20 is 0.35. So I'm going to call this 0.35, just because we're graphing by hand. Okay. Alex likes fractions. So if we're in Alex, we want to have fractions. If we're graphing by hand, we just want to eyeball it. We can just go ahead and use the decimal. Okay. So I'm going to go to my graph now, if you guys are okay with this. And I'm going to find that point 0 comma 0.35, which 0 is at the origin, and then up 0.35 would be like here-ish. And it doesn't have to be perfect, because again, this was just a hand drawing. But 0.35 is somewhere here, maybe a little bit less than the halfway mark. Good to go. You guys okay with that y-intercept? Questions, comments? Okay. Let's get the ball rolling because we got to find these x-intercepts and finish up this graph. Okay. So next on the list is find the x-intercepts. So I think that was, technically it was D, so we're going backwards. Okay. Find the x-intercepts. Okay. And you may have more than one x-intercept. So can you guys remind me, what was the process that we used to find the x-intercepts of a function in the past? I'm going to go ahead and write this function down. It was x squared plus 6x minus 7 over x squared minus x minus 20. Does anybody remember or have any clues? Maybe you want to take a wild guess?
Set it equal to 0.
Yeah. So for the x-intercept, we would usually set the entire function equal to 0. So I'm going to put here, in the past, we set the function f of x equal to 0 and solve for x. However, for rational functions, we just need to set the numerator equal to 0. Okay, so that's going to be a really important key. set the numerator equal to 0 and solve for the x-intercepts. So that's kind of similar to what we did earlier when we found the restricted values. So we set the denominator equal to 0 to find the restricted values. When we're finding the x-intercepts, we're just going to set the numerator equal to 0. Okay. So I'm just going to take x squared plus 6x minus 7 equal to 0. And then I'm going to do the fast factoring method. We'll have x, and then we need a 7 and 1, or a 1 and 7. Okay. And then that's got to be a positive 7 and a minus 1 so that we get the positive 6 there. Fast method. Okay. So if I set these equal to 0 using my zero product property, what are my x-intercepts? X is equal to?
-7.
7,
And x is equal to?
-7, and 1.
And positive 1, right? So those are my x-intercepts. And I could write those as ordered pairs. So that's going to be -7, comma 0. And 1, comma 0. Okay, so that means that I can plot these points now. Okay, so I'm going to bring back my graph. -7 and positive 1. So I'm going to put a point over here at 1. Okay, that's 4, 5, 6, 7. So -7 is here. That's my x-intercept. And then positive 1, comma 0 is right here. Okay. But right now, we don't have a good sense of what this graph is going to look like. Okay. So in ALEKS, and the last thing on this sort of question here, question F, says plot at least 2 points, okay, on either side of the vertical asymptotes. Okay. So that means that if you think about the vertical asymptote as cutting the graph into 3 sections, then I need 2 points that are on the left of -4, at least 2 points that are in between -4 and 5, and then I need at least 2 points that are to the right of 5. Okay. So how we're going to do this is we're going to rely on our calculators. So hopefully you guys have a TI-84 or something similar, because if you have a TI-83 or something that's a little bit different, then these steps won't quite make sense, okay? But what we're going to do here, I'm going to clear my memory real quick. Let me zoom in. We're going to graph this, okay? So what we're going to do is hit the y equals button, so that you get this screen here, which has a bunch of equations. So the y equals is in the upper left-hand corner. Then we need to type in our equation or our function, right? So in that first equal sign, I'm just going to put a fraction. So I'm going to put alpha y equals and enter to get my fancy fraction the same way we always have. Then to type in the equation, which is x squared plus 6x minus 7 over yada, yada, yada. You guys can't see that, right? You use this button here that's next to alpha that has the x, t, it looks like a theta and an n. So I'm going to put x squared plus 6x minus 7 so that my numerator looks exactly like what I wrote down. Then I need to type in the denominator, which is x squared minus x minus 20. Okay. Then I'm going to hit the second button. And then this graph button over here, because I hit second, it's going to let me see the table. Okay, you see the little blue word that says table there? I'm going to go ahead and click on that button. And now I have the table of all of the XY pairs that belong to this function. So I don't have to calculate my Y values or my X values at all because the calculator is doing this for you. Okay. I'm going to turn off that bright light so that you can see this a little bit better. Okay. So for instance, we have 1, 0, which is one of our x-intercepts. And also we have -7, 0, which is another one of our x-intercepts, right? So if we need to get a couple of points that are to the left of -4, then what we could do is, just to organize ourselves, I'm going to write a little table, x, y. And I'm going to choose some numbers here that are less than -4. Like I'm going to choose -5, -6 over 5. So that's -5, -6/5. Okay. So that's my XY pair. I could plot that if I wanted to. We would just have to convert -6 over 5 to a decimal so that we could do that by hand, right? And then I could choose -6 and -7 over 22, but we already have -7, 0. Okay? Because we already calculated that x-intercept. So that will be good for my 2 points over here on the left section of my graph. But I need 2 points for the middle section. And right now, these points are kind of close together. So maybe I'm going to choose maybe like -2. And maybe I'll choose like 4. So I'll go over here. And I'm just choosing these randomly. You could choose whatever you want as long as it's within this section. So I'm going to choose the -2. And I'm going to choose 4 as my x values. Then I'll just look them up on the table. So -2 has a y value of 15 over 14. And then 4 has an x value of -33 over 8. And that'll take care of getting a couple more points here in the middle section. Technically, I only needed 2, but I wanted to see, have a better idea of what that middle section looks like. Then finally, I'll look at my section on the right. So I could choose any 2 numbers over here. So I might choose 6, and then maybe I'll skip 7 and just go to 8. And I'll just look on my calculator here. 6 is 13 over 2. And then 8 is 35 over 12. And like I said, you don't have to worry about what these fractions are because you can convert them to decimals so that we can plot these a little bit more easily. So to get out of this table section, we'll just go ahead and hit the second button and then the quit button, or the second mode, till we get back to the calculator. And now I'm just going to go through this and calculate all of the decimals. So I'm going to go -6 divided by 5. This is -1.2. Okay, this guy here, 15 divided by 14, is about 1.07. Doesn't have to be perfect because we're just doing this by hand. -33 divided by 8 is about -4.125. 13 divided by 2 is about 6.5. And then 35 divided by 12 is about 2.92-ish. Okay, again, doesn't need to be perfect because we're just doing this by hand. But now that I have these points, I can plot them on my graph. Let me zoom out a little bit.
And you said the points have to be in between the ones we already plotted.
They have to be in between the vertical asymptotes. So like something over here to the left of -4, then a couple of points between -4 and 5, then a couple of points after 5.
Okay.
Okay. So you get to choose your x values, and then you're just looking up the y values. Okay. So like -5, comma, -1.2 would be -5, comma, -1.2 is going to be down 1, but a little bit extra, so something like that. So now that I have these 2 points, what I'm going to do is connect them with a curve that kind of hugs those asymptotes. So it's going to curve through like this, and that's what this section of the graph will look like. Then I'll go ahead and plot the middle section, which was -2 and 1.7. So that's going to be -2 and 1.7 is a little bit above my horizontal asymptote. Then we have 4 and -4.125. So 4 and -4. So that's 1, 2, 3, 4, and a little bit extra. So like here-ish. And you can kind of see that this graph looks to be curving a little bit. So I'm going to draw a line that connects these dots like so. There's my middle section passing through all those points that we found. And then the right-hand section goes to 6 and 6.5. So 6 and 6.5 is going to be 1, 2, 3, 4, 5, 6.5. So it's going to be like right here-ish. And then 8 and 2.9-ish. So 8 and 2.9-ish would be close to 3. And then this is going to curve through those 2 points, but kind of hug your asymptotes a little bit. So it's kind of, it's like it's boxed into this corner. Okay. And that's going to take a little bit of time, but if you slowly, if you pick your points correctly here, the way it's going to look in ALEKS is you're going to need to get 2 points. We went a little bit overboard in the middle, but you'll need to get 2 points in between each of these sections that are divided by your vertical asymptotes. But once you type those points in, you're going to click on the graph button and ALEKS is going to draw this for you. So you won't have to draw it by hand. But the nice thing is that if you've drawn this by hand correctly, if you just hit the graph button, your calculator draws exactly what we just drew. Okay, so if you typed in that function correctly into the calculator in y equals, then when you just hit graph, this should look exactly like your hand drawing. And if it doesn't, or if your graph in ALEKS gets really wonky, then you made a mistake somewhere. Okay, and we need to figure out where that mistake is happening because all of these things need to sort of be consistent with each other. Okay. Now, I apologize for going over, but I really wanted to take my time and finish that up without rushing you guys through it so that the recording didn't suffer. Okay, so the good news, if that felt like a lot, is that you can go back and I'll put this recording in Canvas so you guys can watch it later. You can review this graphing section, how we took care of this problem, parts A through F, and then apply that knowledge to the next 2 graphing problems in the worksheet, okay? And so tomorrow, I think at the beginning of class, if you want, we'll go through some of those graphing problems very quickly, just to make sure that we have the correct answers there. But then tomorrow, we're going to focus on the review for test 3. So just make sure, if you want to hold off on this worksheet until tomorrow, make sure you're completing homework number 21 or getting caught up if you've fallen behind. Because tomorrow, I want to give you guys that opportunity to go ahead and get caught up, do the review so that we can have ourselves kind of ready for the test come the weekend. Okay. So if you need to go, I'm sorry again for keeping you guys 10 minutes after, but we'll end it there. If you do have some questions, you're welcome to hang out with me here and chat for a bit, but I'll see you guys tomorrow.
Are you going to be in